last week of Organic 2, we're going to talk about one more class of reaction mechanisms. So if I were to classify the mechanisms we've seen thus far, I'd break them up like this. I'd say most of the reactions that we've seen are ionic mechanisms. So some electron-rich thing is coming after some electron-poor thing. There's probably an ionic intermediate, whether it's a cation or an anion. SN2, carbonyl attacks, pretty much all of them fall into this category. We've also talked about a few organometallic reactions where there's not really that strong electrophile and nucleophile, so like the Suzuki reaction or the Sonogashira reaction where you've got a reductive elimination step like this. That's a little bit different than some ionic mechanisms. We've also talked about radical mechanisms where instead of two electrons at once we have one electron moving at a time, breaking pi bonds in half like that. And then we've seen a few, but not very many, concerted reactions. So in a concerted reaction, we can think of orbital overlap giving us a nonpolar delocalized transition state. And so there's really no ionic sense to this. There's no minus sign anywhere in here. So one concerted mechanism that comes to mind is decarboxylation. So when we have a beta keto acid like this, you might remember me saying it has some weird cyclic transition state. Well, it does. The cyclic transition state looks kind of like this, where I'm forming and breaking a lot of bonds at once. You can see I've drawn arrows here. My arrows go clockwise here, but they don't really have to, right? My arrows could have just as easily gone counterclockwise because it's not like there's a plus and a minus in this situation. Anyways, all of these 6 electrons are moving at once, and that brings us here. And so part of what makes this work is that I'm getting the benefit of new bonds as I'm breaking old bonds. So this isn't something where I have to expend the energy to break a bond before I sort of gain the stability of forming a new bond. I'm essentially paying as I go, both breaking and forming bonds at the same time. The most important concerted reaction is called the Diels Alder reaction. So the Diels Alder reaction, we have a diene, a conjugated 1,3 diene, reacting with an alkene to form a new 6-membered ring. And usually this alkene has an electron withdrawing group on it, maybe a carbonyl, cyanide, nitro, something like that to withdraw electrons to make it a little bit easier. So this is a pretty powerful reaction, right? I usually get excited when I can make a new carbon-carbon bond in a reaction. In this reaction, I'm making 2 carbon-carbon bonds, and I'm making a new 6-membered ring, which I see 6-membered rings all over the place in medicine and biochemistry and so forth. So this is really powerful. Is this thermodynamically downhill? Well, if you look at the bonds we're breaking, the bonds we're forming, we start with 3 pi bonds, right? 1, 2, 3 pi bonds. And we essentially trade those 3 pi bonds in for 1 pi bond and 2 sigma bonds. All right? So while this is technically a reversible reaction, in many cases this is pretty downhill because sigma bonds are generally stronger than pi bonds. So we are trading weak bonds for strong bonds here. Your transition state sort of looks like this, where, again, this is a concerted reaction where all 6 of these electrons are moving in concert at the same time. To understand how concerted mechanisms work, we actually need to look at the molecular orbitals. So remember, way back in Organic 1, we talked about how pi orbitals can overlap and mix. Right? So this is a conjugated system, and these are the 2 highest energy occupied orbitals and the lowest energy unoccupied molecular orbitals. So these are all pi orbitals, and the color here is meant to kind of show phase. Right? So again, when we talked about orbitals, we started by talking about different phases and how blue and red don't mean plus and minus or filled and empty or anything like that. And if you wondered at that point, what do we even use phase for? Why do we care about it? The answer is Diels Alder reaction. So we finally get to explain how we can use phase. So phase lets us understand how orbitals can overlap productively. Okay, so here's our reaction. Here is our diene. Here is our dienophile. Now, I know that I said that when we're talking about concerted reactions, there's not really a nucleophile and electrophile. Well, it's not really true, actually. There's not an ion, generally. There's not something that with a negative charge and a positive charge. But really, every reaction, when it comes down to it, has something that's electron-rich and something that's electron-poor. And even though this is concerted, there's no exception here. And so the reaction here, we're really thinking about interaction between a filled orbital from one, which would be the nucleophile, right, filled electron source, and an unfilled electron, an unfilled orbital from the other thing. Okay, and so I can either think about this overlap or this overlap. It really kind of doesn't matter. But most of the time, what we're thinking about is this overlap here between the highest filled orbital of the diene and the lowest unfilled orbital of the dienophile. Okay, so why does this reaction work? This reaction works because if we look at the phases of those orbitals, they actually match up so that I can make bonds both here and here at the same time. Right? So you might see these S and A's I've written down here. That's symmetrical and anti-symmetrical with respect to the mirror plane. Okay, so imagine I have a mirror going down the line between this thing, pop here. Right? So down here, the left and the right side of this molecule are the same. Right? Blue is on top on both sides. That's symmetrical. Here, blue is on top over here, but red's on top over there. So that's anti-symmetrical. And really the way this is organized, it more or less alternates as it goes up. And the same deal here, right? This is essentially a pi, and that's a pi star orbital. Symmetrical, anti-symmetrical. And so for them to overlap, we need them to have the same orbital symmetry. So orbital symmetry is conserved. Right, so I start with planar symmetry, the same planar symmetry, asymmetry, and both of these things, and my product has that. So the reason that I can have these two things react with each other comes down to the orbital symmetry. Orbital symmetry is what allows this to happen. This molecular orbital picture also explains why I want an electron withdrawing group on my dienophile, because generally the dienophile is going to be the electron poor thing, the electrophile. And so by putting an electron withdrawing group here that can like pull electrons to itself to make its electrons more stable, right? The electrons getting pulled to the electronegative atom are more stable. By doing that, I'm lowering the potential energy of this unfilled orbital. And when I lower this energy, now this overlap is easier because they're closer in energy. And so the reaction is easier. I don't need to get all the way up here. I only need to go that high. So the reason that electron withdrawing groups accelerate this reaction is that we're making our electrophile more electrophilic, right? We're pulling the energy of our electrophile down so it has better overlap with our nucleophile. So again, we really can't get away from thinking about nucleophiles and electrophiles even here where it's nominally kind of a nonpolar situation. Molecular orbitals also help us explain something else. So can I take two alkenes like this and do a similar concerted reaction to get a cyclobutane like that? And the answer is no, this does not work. I can't just heat up two alkenes and get a cyclobutane. Right? So why is that? Well, again, it goes back to orbital alignment and orbital symmetry. Right? To make this reaction work, I would need to have the highest molecular orbital of one side react with the lowest unoccupied orbital of the other side. Right? And if I do that over here, now if I try to make both these bonds at once, here I've got good overlap, but here I've got destructive overlap. Right? So these lobes can't overlap and make a bond. So I cannot do this reaction in one step. Here's an example of the Diels Alder that might be helpful. And this can make really, really complex molecules from pretty simple starting materials. So for instance, here is cyclopentadiene, here is maleic anhydride. They are both achiral small rings. When they get together, I've got a diene and a dienophile. So a dienophile is simply an alkene that usually has some electron withdrawing ring or some electron withdrawing piece next to it. Here I've got these carbon-oxygen bonds pulling electrons away from the alkene. One way to predict your product is to remember that your product has to have this cyclohexene in it and plan accordingly. So that cyclohexene contains 4 atoms from my diene. I've numbered them 1, 2, 3, 4. And 2 of those atoms in the cyclohexene come from my dienophile, the alkene partner. Right? So this is what the ring looks like. Again, these 4 atoms are coming from here. And so now I can start to put on the rest of the pieces. So if I've got this CH2 that's connected to both 1 and 4, I'd better put a CH2 here that connects 1 and 4. If A and B are part of a ring, A and B will still be part of a ring. Okay, so that's a good way to not make mistakes when you're trying to draw Diels Alder products. Is to remember that a Diels Alder product has to have some kind of cyclohexene. And in that cyclohexene, 4 of the carbons come from the diene, right? And the double bond is between essentially what used to be carbon 2 and carbon 3. And the other comes from this dienophile, maleic anhydride. Here's a drawing of this in 3 dimensions. As a side note that we don't need to worry too much about, it turns out that orbital overlap actually gives us the less stable diastereomer. So this little piece in the middle, the dienophile piece, would really rather be sticking out, like equatorial-ish, so it doesn't run into the rest of the molecule. But in the transition state, I've got a little bit of overlap between the p orbital on this carbon and the p orbital on this carbon. And that overlap makes it give us this, what's called an endo product, as the major product. Here's another example. Here's another example of the Diels Alder reaction. Here I've got my trans-trans. Here's another example of the Diels Alder reaction. Here I've got a trans-trans diene, and here I've got an alkyne this time. So the alkyne is different than the alkene, but it still has a pi bond that can act as a dienophile. So 2, 4, 6, arrow pushing, bloop, bloop, bloop. Let's draw our product. So there's our product. It's a new 6-membered ring. The only difference from before is that because I had 2 pi bonds here, one of these pi bonds survives in the product. So I'm making a cyclohexadiene this time. Again, 1, 2, 3, 4, 1, 2, 3, 4. Notice that here my methyl groups are trans, so the stereochemistry in the starting material is set, and the stereochemistry in the product is set, at least the relative stereochemistry. Those methyl groups will end up cis to each other. If instead I have those methyl groups with different stereochemistry in the diene, so this would be EZ or cis-trans, now I would get a different stereochemistry in my product, right? So this is a stereo-specific reaction. I can only get this from that. I can only get that from that. How do I know which one to do? Well, remember that this is a concerted reaction. Everything is happening at once, right? And so there's really no chance for me to scramble any of this stereochemistry. It can only fit one way. And in this reaction, I'm going to be preserving what I can call this plane. All right, so if you imagine that dotted line as a mirror, all right? So if these two kind of have that relationship, if they're reflected into each other like that, then they're going to end up on the same side, right? So if they're reflected into each other, they end up going in the same direction. But if they're sort of asymmetrical, right? If this is not reflected in that, then they're not going to be reflected in the product, right? So again, use this symmetry rule. The plane of symmetry is preserved in this reaction. If these reflect into each other, these reflect into each other. If they don't reflect into each other, they don't reflect into each other there. Here are two Diels Alder products that are kind of complex. See if you can draw what starting materials these Diels Alder products would come from. The first step in answering that question is to find the six-membered ring that comes from the Diels Alder reaction. Remember, every Diels Alder comes from a six-membered, or gives you a six-membered ring. In this case, the six-membered ring, and particularly the cyclohexene I want to focus on, is right, well, I could pick either, but I'm going to start with this one. That cyclohexene right in the middle I want to focus on. And so I'm going to break that down by, I'm going to break this cyclohexene down in really a retro Diels Alder, backwards Diels Alder. Right? So I've identified my six-membered ring, and I'm going to start here at the alkene, push that over, break that bond, and break this bond. And now I'm going to pay really close attention to my arrows and try to draw what that would actually give me. When I break those bonds, I think I get this product, right, where the bond used to be there. This diene I've drawn funky here to match that. But if I kind of stare at this a little bit, I can see that this is just cyclopentadiene, right, a five-membered ring with all kinds of chlorines around it. And then here, I just have really what might be a new Diels Alder product, right? So that's how I might break that down. This one, again, let's start by identifying the six-membered ring. So I've identified my six-membered ring. You can break it down. Again, I like to start from the alkene to draw my arrows. And notice that in this case, this is an intramolecular Diels Alder, right? So it's the same molecule forming a new ring system. Not to keep repeating myself, but look at the increasing complexity, right? Here I have one stereocenter. Pretty straightforward how to get there. Here, it's a lot more complex. I've got stereochemistry all over the place. I've got a polycyclic ring. And so Diels Alder is a really, really powerful mechanism to give me complex reactions. And looking at it from the reverse end, even though this is complex, anytime I see that six-membered ring, especially if it's a cyclohexene, my brain can say, hey, I bet I can make that if I can think about a Diels Alder reaction. And I'll also note that even though there's no withdrawing group on this alkene, right? As originally I started by saying you need an electron withdrawing group. Here you don't, but the reaction still goes well, and that's because it's intramolecular, right? So intramolecular reactions, remember, get a big boost because these molecules are kind of always stuck in the same area, and so they're running into each other constantly. So even though electron withdrawing groups make it easier, if you're doing an intramolecular reaction, you don't necessarily need it. So powerful reaction. And we'll talk about more concerted reactions in the next few videos.